So we want to extend our discussion to discuss the general case of a first order ordinary differential equation. So we have encountered this definition before, y prime, the derivative of y with respect to t, plus p of t, an arbitrary function, times y equals the right hand side g of t as a general form of first order linear differential equation. And it's non-autonomous because the coefficients here depend on t. And so at this stage we can see that t appears on the left hand side, and so in general it's not possible to separate variables, but we can still apply the idea of integrating factor to put the left hand side of this equation in the form of an exact derivative. And so as we did before, we multiply, so we multiply the differential equation by this unknown function mu of t, which is the integrating factor that we want to find. And so on the left hand side we have mu times y prime plus mu times p times y, and on the right hand side we simply have mu times g. All right. And so what we want is, we want this to become mu times y prime. Then we can say that this is an exact derivative of this product mu times y. And so if that were to happen, then by looking at chain rule, the expansion of this would be mu times y prime plus mu prime times y. So this, these two terms must be the same as these two terms that we have over here. You can see that the first term is the same, second term looks different, and so we can make the second terms the same. This coefficient must be equal to the coefficient of y over there. And so exact derivative, we will get exact derivative on the left hand side of the equation if we make that choice. So mu prime equals this mu times p. And so this equation is an equation that we have deduced for this unknown function mu, and we can solve this equation because this equation we can solve by the idea of separating the dependencies. So dividing this equation by mu, we can see that we can rewrite this as log of mu, the derivative of that, equals p. If you expand this, you would see that that equation is same as the original equation that we have, and therefore we can integrate this equation, and so we can therefore get that log of mu is going to be the integral of p, so p t dt, and we can integrate, say, from 0 to some t, and we can say that this is from 0 to t, and 0 is equal to this right hand side. And so just writing that out, we will see that log of mu minus log of mu at 0, and we can choose mu to be 1 at t equal to 0, so that value is log of 1 is 0. So we simply have log of mu equals this right hand side, and so taking exponential gives us mu equals exponential of this expression, so 0 to t of p of t dt. So we have found the integrating factor, and so we can now put this back in the equation and work with the equation. So remember that the left hand side of the equation is now in exact form, the right hand side of the equation is mu times g, and so we have mu times y prime equals mu times g, where mu is now a known function and g was already given when we started the problem. So right hand side here is known, and so we can integrate this because now the left hand side is an exact derivative, and so therefore we have mu times y that we want to find minus the value of mu times y at time 0 when we integrate the left hand side. This is going to be equal to the integral of the right hand side between time 0 and t. So we can say between 0 and t, and just to get the notation completely free of any ambiguity, we can say that this integration is carried out over a dummy variable t dash, which is varying over the interval 0 to t. So that's the integral of this product over the interval 0 to t. So this is now almost the final form of the solution. All we have to do is move these things over to the right hand side, and remember that we had previously already assumed that mu of 0 is equal to 1, and so then the final result, simply rewriting this, is going to be that y of t is simply equal to y of 0 minus this integral 0 to t of mu t prime g t prime dt prime, whole thing divided by this value mu of t, which we have already determined. So we can put this in a box, and that's the general solution to the first order linear differential equation, and we have obtained this using the integrating factor mu of t, which we had found, and here is the explicit expression for mu of t, which is to be plugged in over here. So that completes the solution for this differential equation in general form. Of course, for particular cases, the values of the function p, the value of the function g would be specific, and therefore the integrating factor will be a specific function, and of course the initial condition will be given in a particular problem, and so on. So we can apply this method in general to the first order linear differential equation.